Good afternoon, and thank you for joining us for the 21st webinar in the Offshore Wind series, Learning from the Experts. I'm Kate McClellan-Press, Senior Project Manager in Environmental Research at NYSERDA, and it is my pleasure to be joined by today's experts, Brandon Capasso and Donald Bullen with the Weather Routing, Inc. Before I introduce our speakers, a few reminders for participants and some background on this webinar series. Next slide, please. First, if you are experiencing any technical issues, please contact Sal Graven at the email address on the bottom of this slide. This webinar is being recorded, and the recordings and presentation slides for all webinars in the Learning from the Experts series will be available on NYSERDA's website at the address on this slide. All participants have been muted. We will have time for Q&A following the presentation, so please use the Q&A function to submit your questions for the speakers. Next slide, please. New York State is working to advance the responsible and cost-effective development of at least 9,000 megawatts of offshore wind by 2035. Offshore wind is a critical component in achieving the state's goals of 70% renewable sources of electricity by 2030 and 100% zero emissions electricity by 2040. While offshore wind has been providing clean energy to other parts of the world for several decades, this industry is brand new to New Yorkers. To provide interested stakeholders and members of the public with accessible, impartial information and opportunities for engagement on specific topics of interest, NYSERDA is hosting this educational webinar series called Learning from the Experts to connect the public with independent experts in key topics in offshore wind. We endeavor to select learning from the expert speakers based on their expertise, not necessarily for an alignment of opinions with NYSERDA or the state of New York. If you would like to suggest a topic or speaker for a future webinar, you can email us at offshorewind@nyserda.ny.gov. Please note that the views and opinions expressed in this presentation are those of the presenters. Next slide, please. It is now my pleasure to introduce Brandon Capasso and Donald Bullen. Brandon is the director of both WRI's Energy and Commercial Shipping divisions and has over 15 years experience providing consulting weather forecasts, decision support, weather routing, vessel performance analyses, climatology reports, and forensic weather reports for various clients worldwide. Additionally, Brandon designed and built WRI's in-house weather and ocean modeling systems, which provides WRI's team of forecasters with the best technological tools possible to help protect life and property at sea. He is also an expert on climatology and has prepared hundreds of climatological risk assessment reports for various locations around the globe. Donald Bullen is a maritime meteorologist with a keen interest in climate and advancing clean energy in order to combat climate change, while ensuring that good paying jobs are available in the energy sector. Early in his career at WRI, Donald took on a role in the energy division and helped create the company's presentation for the 2020 AWEA poster by developing an analysis of the impact of significant waves on floating wind farms. Donald was recently promoted to project manager of WRI's energy division. Thank you all for joining us today. And now over to you, Brandon and Donald.
So good afternoon, everybody. I'm Brandon Capasso, director here at WRI. So I'll start by just giving you some history about our company. WRI has been in business since 1961. The company was founded at the advent of the satellite era. So as soon as weather satellites started going into space, that made it possible for a company like us to provide a weather service for ships that are around the world's oceans. We've been providing weather routing services, decision support, vessel performance analysis, among other things, for more than 60 years now. We currently employ 50 marine meteorologists. All of our meteorologists have at least a minimum of a bachelor's degree in meteorology. And our operations center, our headquarters, is staffed 24/7, 365 days a year. You can reach a meteorologist on the phone here 24 hours a day. We are located on the Hudson River in Glens Falls, New York. The company has always actually been based in New York since it was founded. Originally, it was New York City, and then it moved up to Glens Falls. Okay, so I'm going to pass over to Donald here. He's going to go through the first stage of our weather impacts. So go ahead, Donald.
Hello, I'm Donald Bullen. And as Brandon said, we're going to go through the first stage of weather impacts. So the first thing we're going to talk about is rapid cyclogenesis, also known as bombogenesis. You can also frequently in our area hear it referred to as a nor'easter. However, not all nor'easters are bomb cyclones, and not all bomb cyclones are nor'easters. So with all that out of the way, the first ingredient for the generation of a bomb cyclone, which is a cyclone that intensifies or strengthens with the surface pressure decreasing by 24 millibars over 24 hours. First element of that is an upper level large scale trough approaching the eastern United States. You can see in this schematic here, highlighted in green, is the area where you are likely to see a potential low pressure system forming at the surface. And the next element of that would be a phased interaction between the northern and southern jet streams. They tend to be independent of each other, however, they can collaborate. And in times of collaboration, that can help the bombogenesis or generation of a bomb cyclone. And the third element of that would be an Arctic air mass associated with an upper level trough. That is frequently referred to, if you see it on the news, if you're watching the weather reports or something like that, they'll typically refer to that as an Arctic air outbreak or a Canadian high. A frequent occurrence or a way to associate this is during the dead of winter, especially if you're in upstate where it gets, really cold during the dead of winter. That's when you have those really clear days, bright sunshine, but the local temperature is typically in like the low 10s to single digits for a daytime high. That is an Arctic air or Canadian ridge coming in. They tend to originate from areas such as northern Alberta, northern Manitoba, Canadian Shield, and come into our area, and that can help with the other aforementioned pieces to generate a bomb cyclone.
And sometimes that area is actually referred to as the polar vortex, which I think that word gets thrown around a little bit too much in the media, but sometimes that cold air is actually an extension of the polar vortex, as was the case in the example that we're going to show here shortly.
And the fourth and final element to that is interaction with a comparably warm ocean, which is aided by the Gulf Stream. As you can see in the schematic here, this is temperature of the sea surface, and you can see this conveyor belt of warmer water being brought up from more southerly latitudes. That's the Gulf Stream. That's a very strong and well-known current that's off of the eastern seaboard of the United States, and that can help with the generation of bomb cyclones as well.
So I'll take over here. This is something I wanted to share because it's relevant to the topic of bomb cyclones. This is actually a graphic from one of my college textbooks that I scanned and put into the presentation just because it's research that was done by two highly regarded meteorological researchers back in the 80s, Paul Cochin and Louis Ussolini. And so what this is showing is they studied a group of bomb cyclones off the East Coast between 1970 and 1985. And to meet the criteria for their study, the system had to strengthen at least 1 millibar per hour over the course of 3 hours. So what this shows is the track of every cyclone that met that criteria in their study. And really what this shows is that the most intense storms, the storms that typically become bomb cyclones and rapidly intensify, follow a track generally from the Carolinas northeastward, often to the areas adjacent and east of New Jersey, out to Cape Cod. And so right off the bat, this is right where the areas, all of the least areas are for offshore wind currently. And so that's a clear and present hazard, right off the bat. The strongest lows occurring anywhere in the Western Atlantic and the Eastern United States are happening right there in that area. And I'll zoom that in here, and I overlaid the current least areas on the graphic. And you can see these systems are in the process of peaking in strength and rapidly intensifying as they're moving through this area, which creates a scenario where you have generally unpredictable short-term conditions. We can predict the occurrence of a bomb cyclone well out, several days out. But as far as where the highest winds are going to be with respect to that low, that can change in real time on an hour-by-hour basis even. So this is a really neat graphic that we put together. This is a blizzard from January 4th, 2018. Really a classic rapidly intensifying cyclone. The colors on this graphic represent wind speed. And so if you look at the bar on the right side of the screen, that's the wind speed in knots corresponding to the colors. So you can see, this system formed and very quickly was producing winds in excess of 85 to 95 knots across the southern periphery. This storm was particularly notable because it actually broke records. The system deepened by 53 millibars in 21 hours. So it was double the rate of intensification that you would need to be classified as a bomb cyclone. This was actually the fastest observed recording of intensification in modern times over the Western Atlantic, and actually ended up being one of the strongest non-tropical low pressure systems ever observed in the Western Atlantic. The second animation is similar, but what we're doing here is we're freezing the highest wind speeds over time. And so you can see everything's kind of accumulating as the storm moves north and sitting still. So that shows in the end, you're left with what was the highest wind at any point in this graphic by the time the storm was over. And you can see across the lease areas, we're talking about 65 to 75 knot winds, pretty much over much of the lease areas. And that's sustained. That's not even accounting for the gusts. That's a sustained wind. And there was likely pockets of higher winds, even up into the 75 and 85 knot range. What was particularly interesting about that storm, and really a characteristic of that we often see with the strongest bomb cyclones, is what's called a warm seclusion. That's a meteorological term that I'll explain here in a series of graphics. And so this isn't off the East Coast. This is actually up over the North Atlantic, but it's a great example of a warm seclusion. So that's why I'm using this one. So you have a low, you have warmer air on the eastern side of the low, colder air wrapping around the western side of the low, and then you can see the warm front and the cold front here, representing where those air masses are trying to advect, or where they're trying to move. And so the warm air is trying to push northward, the cold air is trying to push eastward. What happens is the warm air gets pulled so far north that your warm front actually starts trying to push back westward into the colder air that's present to the west, which it can't do because the cold air is more dense. And so you end up with a lot of precipitation, and you can see that in the cloud field here. But the warm air kind of gets stuck there. At the same time, the cold air is still progressing eastward, south of the low. But you still have this area where the warm air is stuck to the north of the low, and you get what's called a cold frontal fracture. So the cold air is now advecting eastward, but it's not really advecting eastward south of the low anymore. It's really separated from the low, and it's just pushing eastward on its own. And then the final frame here shows a separated cold front, and the cold air is actually now starting to wrap back in the northern side of the low, but the warm air is still stuck in the middle of the low. And as it gets surrounded by that cold air in the low circulation, that provides a mechanism for the low to rapidly strengthen, deepen, and producing hurricane force winds around the low in a symmetric fashion. Actually, when systems do this, they often take on the appearance of a subtropical or tropical cyclone, as did the storm on January 4th, 2018. It actually had an eye feature, and it was producing deep convection or thunderstorms around the center, similar to what a hurricane would do. So the impacts on bomb cyclones, or on offshore wind from bomb cyclones, obviously the safety of operations and maintenance crews, construction crews, transport, really any other working crew is going to be affected by these storms. It creates a 24 to 36 hour period, if not longer, where nobody can do anything. So you have downtime for both the crews, you have downtime for the turbines. If the wind speed is high as what was shown before, the turbines can't really operate, so everything is kind of shut down. That affects power production. So needless to say, accurately forecasting the wind and the sea conditions associated with these storms is absolutely crucial for both of the above points. The forecast has to be on point to handle these, or else you can end up with disastrous situations, damage to property, and even loss of human life. So long-range predictions, which is something we can do here, and we'll explain that in the coming slides. Long-range predictions can really optimize the scheduling for the above task. Organizing this downtime, planning well ahead for these types of storms really can save a lot of money. So you don't have to pay people to be on standby to work if you know something is coming and they're not going to be able to work anyway. And that's really where our consulting services come into play. So I'm going to go through a series of slides that just kind of explain, how do we predict these things in both the long range and the short range. And so hopefully give you guys some insight on what it is that we do here when it comes to forecasting. So in the long range, we typically use what are known as climate models, popular climate models, the CFSR version 2, or the CFS v2. And when I look at climate models, I'd like to look at 500 millibar height anomalies, which is how far is the height of the 500 millibar pressure surface from normal, from a climatological normal. And that's what this plot is on the right here. What that tells us looking ahead, because these climate models can actually handle these upper level long wave patterns well out in time, up to 3 months. You're not going to get a perfect forecast of temperature at the surface from a model at 3 months, but it can actually handle these long wave upper level patterns pretty well going out, 2 to 3 months. And so we look at trends. We look at, how are the models changing? How are these climate models changing their solutions or on a day-to-day basis? And when you start to get consistency in the long term, that really tells us a lot about what to expect going forward in the long range, the 2 to 10 week period. Another thing that is related to this is teleconnections. The best way to explain teleconnections is basically, it's like the butterfly effect, but it's not a butterfly. It's something that's very large, hundreds of miles, like a thunderstorm complex in the MJO oscillation in Indonesia. And that's what this purple shaded area over northern Australia and Indonesia represents, the MJO. And really what that, to put it simply, it's a stormy pattern that occurs. There's a lot of thunderstorms, kind of a monsoonal type event. And what that does is it sends a lot of moisture up into the central Pacific. So if you follow the arrows up from there, you see this green shading in the central Pacific. And that's all moisture coming out of the storm complexes in the MJO. And that moisture actually can then turn into what's known as an atmospheric river that streams all the way up to the western part of the United States. That feed of moisture then can provide any lows that are developing in the winter months in the Gulf of Alaska with additional moisture and energy to strengthen further. And so almost every bomb cyclone that we see off the west coast of the United States is assisted by that atmospheric river of moisture. And in turn, you get a deep trough in the western United States when they're being impacted by a storm. The counter effect of that is a ridge in the eastern United States and above normal temperatures for the winter months. So that's just an example of how teleconnections work. Something that happens on the other side of the world over the course of several weeks can actually have significant impacts on what the weather is in the United States or elsewhere. Moving on to mid-range forecasting, 4 days out to 2 weeks, we typically would use global models known as the GFS. Some of the models that most of us are more familiar with in the public, GFS, the European, the ECMWF. The Canadian now has a model called GEM that's significantly improved in the last several years. And this graphic on the right is neat because it kind of shows how weather models work. What you have is a grid, but it's not just a two-dimensional grid in the X and the Y. It's actually a three-dimensional grid. So picture just a bunch of cubes laid on the surface of the Earth, and those cubes collectively represent the depth of the atmosphere. And so on a supercomputer, you can actually simulate weather processes in each one of these cubes and then pass that information on to all the adjacent cubes in the grid. And that's essentially how a weather model works. That's how a weather model can predict what's going on and what's to be expected downstream from whatever it's modeling in any given grid point. Another thing that we like to use is sea surface temperature anomalies. And so what this is a map showing how much the temperature of the ocean is above or below climatological normal at a given time. And so the colors that you see that are more orange and red are like +2, +2.5 Celsius warmer than what would be considered normal. This is actually a La Nina. You can see this cool band of water off of the western part of South America. And that's very characteristic of a La Nina pattern. But most of the world right now, at any given time, if you look at sea surface temperatures, most of the world is above normal by at least half to 1 degree Celsius from the previous climatological norm, which is most of the 1900s to around 2000. Short range, 6 hours out to 4 days. This is when we start to look at mesoscale or microscale models, the rapid refresh HRRR, WRF models, which we run in-house at WRI. And then the NAM Nest, the Icon model, is a really nice European. It's actually run by the German Weather Service. Very nice model for mesoscale, particularly when forecasting in Europe. And the Canadian GEM RDPS is also a really high quality actually a mesoscale model. So these come in really handy when we're doing this short-term forecasting, because we can see not only what the large scale features are doing and where they are, but what they're doing at the surface. What are they causing to occur at the surface, right? Are they producing thunderstorms, severe thunderstorms? Are they producing high winds? The meso and microscale models allow us to see that, in a shorter range. And it's not to say that they're perfect. As I said, oftentimes they're not perfect. But knowing the trends and understanding the biases is really where these tools become useful to us as meteorologists. And we do that by comparing output with observations, surface observations, upper air observations, satellite measurements, ship and buoy observations, and even aircraft observations. And we can actually put these into our internal WRF model and correct the initialization of the model based on what's observed. So that helps to improve the forecast going out in time. Then, as I said, forecast skill, using all the above tools is crucial when it comes to short-term forecasting. Being able to put together all the pieces of information that we have, all the tools that we have to be able to predict what's going to happen at a given place and time. And then the last is nowcasting, basically monitoring an active weather situation 15 minutes out to the next 6 hours. This is when we start to use radar, satellite observations. Radar is a really nice tool, and it's probably one of the most useful tools when it comes to predicting what's going on in the near term. We can also use microscale models. This is a microscale model over the Eastern Mediterranean during a wind surge in the Aegean Sea. And again, the benefit of microscale models is that we can plug in these observations that we're getting from surface, from upper air, from ships and aircraft. We can plug those right into these microscale models and say, here's a corrected grid point based on what was observed. And again, that can really improve the quality of the forecast that comes out of the microscale models. Another thing that we always say as meteorologists, just look out the window. If you're nowcasting, that becomes a really important factor. What's happening outside right now? Is that what's supposed to be happening? And I realize, when it comes to forecasting for offshore, we can't just look out the window and see what's happening 40 miles offshore. But webcams have actually kind of fixed that problem in the last few years. There's a lot of webcams that have the ability to stream live from really anywhere on Earth using things like satellite uplinks for internet connection. And this really helps. I often use webcams when we're actively forecasting a landfalling hurricane, for example. And we have clients that are in port and tied down because they're not expected to take a direct hit. For example, they decided not to evacuate and they're just going to hunker down and ride out the storm. It's really nice to be able to zoom into that area with a webcam and see, okay, what's going on here? Are we starting to see any damage or anything that would warrant us advising our client that things are getting worse, and just having that tool available is really nice. So I'll pass over to Donald to discuss the next hazard of icing and freezing spray.
All right, and so as Brandon said, I'm going to be discussing icing and freezing spray. In a similar fashion to some of the elements of the genesis of a bomb cyclone, one of the main causes for this is potential for very cold air temperatures during our cold months, peak winter. And that's going to interact with a comparatively warm ocean of about 40 to 45 degrees Fahrenheit. And that very cold air and also high winds are going to provide a mechanism for airborne supercooled water droplets or sea smoke that are going to want to freeze on contact when they meet the first item, in this case, typically a wind farm. And part of the reason for the strong increase in winds is when you have these cold air outbreaks, it's a very strong ridge of high pressure. You have a sharp pressure gradient at that point that's going to create strong winds. And a really good way to visualize this is if you were to go outside on one of the coldest mornings of the winter with a pot of hot water and leave it sitting out there, you're going to get some super cooled water droplets that are going to rise and want to freeze on contact with the first thing that they would come into contact with, which in this case would be a wind farm. And that can provide all sorts of logistical nightmares and damage, or not as much damage, but definitely an adverse effect on the performance of the turbine, and a safety hazard as well for workers and people around the area.
You definitely, I'm not sure what they're doing with current construction, if they're installing de-icing. I hope, we have done some studies for some of the organizations that are developing offshore with regards to freezing spray, but you really just have to do your homework there. In this case, off the east coast of the United States, the northeastern coast of the United States, it is cold enough to have icing on turbine blades, especially when you consider, as Donald said, the warm ocean. And what we'll show next here is the minimum temperature from 2013 to 2017 in this area, which we actually modeled in-house to demonstrate. And I'll let Donald explain that further.
Yep, so this is an in-house model of 2013 to 2017 minimum temperatures at 100 meters of altitude, or typically right around where the hub level of a turbine is. And so as you can see in here, we have, again, superimposed onto this image the cutouts of the lease areas. And even in the warmest pocket here, you're still looking at a minimum temperature of about 5 degrees Fahrenheit. And going down from there, I mean, you go into the New York Bight, and you're looking at conditions approaching, -6, -7, -8 Fahrenheit. And so that's a very sharp contrast between the ocean and the air temperature at that point. And so as you can see on the next slide, what that's going to produce is ice accretion, especially with these stronger winds. The first one, the first graphic that I'll draw your attention to is Rime ice accretion, which is more likely to be the scenario that would happen in these events off the eastern seaboard. At that point, you have a very low moisture content in the air. We're talking about 0.3 grams per cubic meter. Air temperature of about -10 degrees Celsius, and a wind speed in this demonstration of 40 meters per second, or about 80 knots. And so you can see it's a very, very fine, smaller grain ice accumulation. But again, as the conditions continue, this can really start to build up and impose problems. The other one that we're showing here in the demonstration is glaze ice accretion. That has a 10-fold higher liquid water content of about 3 grams per cubic meter. The temperature in this example is about 5 degrees below 0 Celsius, and we're same wind speed. So you can see that it's a lot more moisture-heavy ice accretion. But again, most of the cases that you would see on the eastern seaboard would be of a Rime ice accretion variety.
Yeah, to give you an idea, the 0.3 grams per cubic meter in the top example is similar to what you would have. That's about the water content that you would have in fog or inside a cloud, non-thunderstorm cloud, about 0.3 grams. So sea smoke is fog. And so this would be, the top example would be a comparable situation that would actually be probably quite likely to occur during the winter months over the current lease areas off of New England and in northeastern United States. The 3.0 grams per meter cubed is a lot of moisture. That's more like what you would see in a thunderstorm even. It's very, very rare to have that much water in the air when it's that cold, but not to say that it can't happen, particularly when you start to involve sea spray during high winds. So the third hazard here that is kind of related to the cyclogenesis, but more the conditions that are produced by the cyclogenesis. The areas off the northeastern U.S. and New England are well known for having confused seas. And the reason for that is because you can have various swell systems simultaneously impacting areas at the same time. So you could have a large storm off of Newfoundland in Canada that's producing heavy east-northeast to northeast swell that's propagating southwestward, into the northeastern United States. And then at the same time, you could have a developing low south of the Carolinas that's producing east or southeasterly seas or even swell, depending on how long or how slow the low is moving. Then as the low comes up the coast, you start to introduce a south and southwest wind sea and even a west and northwest wind sea. And so you end up with a situation where you have waves coming from every direction. Some of them are as high as 2.5, 3 meters coming from opposite directions. And that instantaneously creates a situation where it's very hard to handle a vessel, especially if it's a small vessel, like a support vessel or an OSV. Going out and maintaining these wind farms in sea conditions like that is not really an option. So you further complicate that, you have interaction with Gulf Stream loops, so loops that kind of spin off the northern side of the Gulf Stream, and tidal currents in and out of some of the bays along the East Coast because the water is generally shallow on the continental shelf, which is why we can put these wind turbines in the ground. But at the same time, that shallower water creates a situation where you have more of a component of tidal currents. So when the tides go in and out, you have movement of water that contributes to the overall current that's present. And if the current is opposite the wave direction in any case, it actually can create more of a hazard. It creates a steeper wave, it creates a higher wave, and it makes it more likely that the waves are breaking. And it can even in some cases create what's called a standing wave, which is a wave that is almost to the person on the water. It looks like it's standing still as the current flows through it. Confused sea states, as I said, particularly dangerous to small sensitive vessels. And situations where you have confused seas, particularly when you have waves that are opposite one another, increases the likelihood that wave sets will be higher than the significant wave height, which is defined as the highest 1/3 of waves present at any given place in time. So it increases the likelihood of exceeding that. And then on top of that, it even increases the possibility of the occurrence of rogue waves. So this is a buoy measurement, an instantaneous buoy measurement from a NOAA buoy that can actually record the full wave spectrum. So it's not just measuring one wave direction, one wave height. It's looking at how is the entire sea state right now, up to 25, 30 different waves that are happening, some of them which you may not even notice, and some of them which are obviously more significant. So each one of these orange star type icons represents a wave set that's present at that location at that time. And for reference, this time is actually during that January 4th, 2018 bomb cyclone. Right at the end of it, at the peak of wave conditions is when this observation was taken. And so each one of these waves corresponds to a period on the bottom. So the shorter period waves are located on the left side. And the longer period heavy swell waves are located more in the middle. The height on the graph or the y-axis represents the approximate wave height based on the energy that's measured in the wave. So what you have here is you have a wind wave from the north-northwest to north-northeast at about 1 to 3 meters. That's being generated by the local wind. It's very short in period, around 6 seconds. Then you have 3 to 5 meter waves at about 6 to 10 second periods. And then you have 6 to 11 meter waves at about 10 to 18 second periods. And that's the heavy swell. So you have 3 distinct directions here and all of those waves. Could you imagine an 18-foot wave from the northeast at the same time as a south-southeast wave at 10 meters? It's a pretty rough situation that you don't really want to be in when you're in a small vessel, really any vessel for that matter. Again, the currents can really affect the wave heights. I explained that a little bit before, how this interaction can increase the wave height and the steepness. This is an example here of tidal currents going in and out of Delaware Bay during the tidal ebb and flood. And if you had a heavy swell propagating in from the east here when the tide was going out, you would end up right off the point here at the entrance of the bay with some pretty hazardous conditions. The swell could increase in steepness and in height up to a meter or two, if not more. And we see this in the Gulf Stream all the time. We've been dealing with that here for a long time with our yachting division. We often have clients that want to go back and forth from Florida to the Bahamas. And this is an actual photo taken from the Gulf Stream in a strong northerly surge in the late autumn. And so you can kind of see in between each of the waves, they're so steep you can't even see down what's on the other side. And the reason for that is because the current is flowing directly opposite to the wave heights and creating these steep, slow moving waves. And so again, this increases the likelihood for a rogue wave to occur. definitely poses a hazard for O&M, construction, transport, really any operations that are happening offshore if you have a situation where you have currents interacting with the waves. Another important note here is tidal current is not accounted for in most long-term model wave climatology. When you have an assessment done, and they're doing an assessment for the waves, like the ERA5 is a popular one, those wave heights are not accounting for tidal currents and the effects of tidal currents near the coast. How do we forecast the sea state here? Well, we run a state-of-the-art model, accounts for up to 25 different wave spectra or wave sets. And then we actually couple this wave model with our atmospheric WRF model and a high resolution tidal current / ocean current model globally. And so we're able to take account of all these factors that we just talked about in our wave model to produce a really highly accurate sea state forecast. And we can provide multiple parameters. We can provide customized parameters. We had somebody recently that looked for, they wanted wave length in their forecast. So the length between the crest of each wave. And we were able to provide that just using output from our wave model. Just a quick schematic of how our modeling system works. You have all the input, topography, land use, currents, sea surface temperatures, observations, aerosol concentrations. All of that goes into the model itself. And then we run the regional local models, which the coverage is kind of small here, but you can see where we're running those models now. And then we feed that into our high resolution wave models along with the currents to come up with a good forecast. And this is actually a screenshot from our Smartwin Portal. This is our site that subscribers can go on and look at a multitude of weather data that we're producing in-house, some of the stuff that we're getting from outside. We recently just put European ECMWF data on here. And so really encourage you guys to reach out and check out our Smartwin Portal. It's a really nice place to get a kind of one-stop shop for anything weather when it comes to forecasting and give you access to really the high quality data that we're producing here. So the final section here is tropical cyclones. We got about 4 minutes left, Donald, so you might have to rush through it a little bit, but go ahead.
All right. So as Brandon has mentioned, I'm going to talk about tropical cyclone impacts. So typically when one of them impacts our area, there's a phenomenon known as ridge blocking that happens. That's when you have a continental high pressure system, or again, one of those Canadian air outbreaks over the mainland United States, blocking the system from moving inland of the United States and actually bringing it up the eastern seaboard. And during the late season, systems can interact with Arctic air masses, again, from the Canadian continental Canada, and produce large, powerful systems such as Hurricane Sandy 10 years ago that really strengthen a lot during their time of extratropical transition, or when they become a more traditional cyclone and not tropical in nature. And despite us here being, well into the extratropics in the New York State and southern New England, there's still an average frequency of about 1.6 systems that across the lease areas per year, as can be seen here in this schematic. This is a drawing of, or a documentation of all systems that pass within 150 nautical miles of the Hudson Canyon. And zooming in on it further, you can see some, on the next slide, you can see some pretty well-known systems. So some of them would be in recent memory, and some of them are in memory for people who've been around a longer time, like such as Hurricane Agnes back in '72 caused a lot of flooding in New York State, such as around like the southern tier and other areas. You can see here Hurricane Bob back in 1991 approached a lot of the lease areas, especially in the ones near Block Island, and actually went pretty much right through Block Island back in '91 as a Category 2. Other well-known names here, such as Irene in 2011, coming up the New York and New Jersey bight, also created a lot of local hazards and mayhem. And so this is a schematic here of Hurricane Sandy, again with those freeze frames of peak wind speeds. You can see about conditions actually getting up towards 100 knots, and localized conditions of about 80 knots through 70 to 80 knots through a lot of the lease areas, and an area of an enhancement in the New York State bight of in excess of 80 knots. And so these are definitely conditions that can happen, and we need to, be prepared. And so on the next slide, you can see This is an example of some of the damage that can actually happen from tropical cyclone impacts. This is from a Category 4 typhoon off of one of the Japanese islands. It is noteworthy that none of the systems in that past graphic were Category 4 or higher, but that's not to say that can't happen. And either way, Category 2, Category 3, you're still going to have the potential for wind speed to exceed the design limits for turbines, resulting in damage and destruction, potential for high wave heights to exceed the foundation and tower design load limits. And even if it's not all that severe of a system, you're still going to have significant downtime for operations and maintenance, construction, transport, and power production. And just conditions aren't safe for people to be out there in. And so there's downtime. You can't really do much during that period of time.
And again, to emphasize, that's 1.6 times a year. So almost every year there's one, and if not two, and so that's two separate several day periods that you're dealing with impacts from these systems.
And so where we come in is one of the things that we do in our forecasting packages for clients is tropical analysis. And we actually issue track and intensity forecasts as much as 3 to 5 days prior to government agencies starting to issue advisories. We're open 24/7, as we've mentioned, and we always have somebody looking at all ocean basins. And if we see any area of which there's a reasonable degree of confidence that there's going to be tropical development, we create what's known as a tropical low in our system and start issuing advisories on it that take into account the position, strength, and track of the system. We also offer consultation services, which include when and where to move, when is it safe to return, and how will this impact operations. And we've been providing this sort of surveillance and services to many companies and clients on a continuous basis over the past 10 to 15 years.
Yeah, and that's single clients. Like, we actually have people that have been under tropical surveillance with us for 15 years, and because of that, they've never had an incident or an accident because they're planning ahead, they're preparing, they're doing the necessary things to make sure that they don't end up in a situation that they can't get out of. So we'll sum things up here and we'll open up for questions after this. I just wanted to run through the conclusions here. Obviously, as we've shown, a wide variety of weather hazards exist offshore from the Northeast US. And we want to emphasize having a weather expert involved in the discussion is crucial for making productive decisions, either whether that's regarding operations, maintenance, construction, surveys, anything. If weather is a concern, it's always good to have someone that's an expert involved in that conversation. Our meteorologist here, we understand complex weather factors in the forecast, like gust duration. You can say it's gusting to 25 knots, but how long are those gusts happening, and when do those gusts become more of a sustained type wind impact? Ocean wave spectrum, as we touched on before, depth of the marine boundary layer, which can have significant impacts on the wind speed that actually materializes in a stable condition. Our services are customizable, so really anything that would be considered a weather requirement on your end, we can do it. Even if we don't have a specific service in place for that right now, we can customize our services to meet what your needs are. If you need a special weather parameter, or there's an infinite number of combinations of things we can do. But when it comes to resource assessment, for instance, pretty much every report we do is customized in that regard. We have more than 50 meteorologists on staff around the clock, as we said, and then our tropical surveillance, like I said, is a very valuable tool for advanced planning and avoidance of tropical cyclone impacts. On our final slide here, I'm just going to leave our contact information so that everybody has that. Kind of a neat pair of pictures here too. This is a old photo from WRI operations in 1961 when the company was based in New York City. And then here on the right side is a picture of part of our headquarters from 2022. So the business has been operating continuously for more than 60 years, which is something we're very proud of here. So with that, I'm going to stop sharing my screen and we will open up for questions.
Thanks so much, Brandon and Donald. That was a really interesting overview of weather forecasting and all of the kind of hazards that we have on the East Coast. So I'm going to open up with a couple of questions that we've been getting. And I wonder if you could kind of speak to how current, existing offshore industries or the maritime industry utilizes weather forecasting in terms of, safety and planning?
So the way that we've experienced that is really site forecasting is a big one, where we're updating a site forecast on a twice daily basis, which is then being distributed to all of the necessary individuals, whoever's captains of the ships and the operations team and whoever's planning logistics. And so that's really, I would say, the most popular service right now that we're providing. We really don't have a lot of O&M going on yet, just due to the lack of, operating wind farms. That will be something that increases going forward. And when it comes to O&M, I think what we're going to see is a lot of consulting services being needed, where we'll get a call in the morning and they'll say, hey, we're not sure if it's safe to go out today. What do you guys think? And we'll try to get, at that point, hopefully we already have operating constraints, and then we can say, you're right on that line. And sometimes when you're right on that line, as I said, when you have a situation like you have interacting wave sets or different wave sets, you're much more likely to have a wave that's higher than what's expected. And that's the kind of information that we would convey to the client at that point, that yes, the official forecast is showing a significant wave height of X feet high, but there's a high probability that wave heights will exceed that, more common than what you would normally see in a less tumultuous situation. So.
Thanks. And then turning over to the offshore wind industry, can you talk about anything that we've learned in your industry, if anything, about how weather has impacted existing offshore wind developments and operations in Europe?
So there's they kind of played that. So they pioneered the whole thing, right? In Europe, when it comes to offshore, they were the first ones to really do it on a large scale. And it did feature some growing pains. There was a couple instances in the North Sea where several turbines were damaged or destroyed, leading them to, I guess, realize that maybe they need a little bit higher of a load limit, stronger materials and things like that. So we're lucky, I think, here, in the northeastern U.S. where we're doing this now, because we don't have to go through all of those pains that they went through in the European industry, because they've learned from their mistakes and we can learn from their mistakes as well. And I think a lot of that comes down to just being prepared. Making sure that you know what to expect in a worst case scenario, and then making sure that planning wise, everything is in place to prevent putting somebody in a dangerous situation or creating a situation where you're going to have damage to property. But again, I think a lot of the bad things that happened, not that there was a lot of bad things that were happening over there, but there were definitely issues that they had to overcome. And as I said, we ourselves can learn from that, here in the northeastern U.S. too.
Yeah, it's a lot less trial and error
Right.
in the eastern seaboard of the United States, because of similar depths as to a lot of the North Sea, and some fairly similar climatic features actually. And so we're able to implement a lot of what they've already learned and established into our systems here.
And I think based on, the weather hazards that you were talking about, and maybe taking some of that learning from, how they have dealt with that in Europe and in other industries in the US, are there estimates of, how many days a year that hazardous weather would actually impact turbine functioning, or, ability to be on the water for maintenance activities?
Yeah, and so that comes down to resources, or not resource assessment, sorry, downtime assessment. And so what we will do is we never look at just one data set when we're coming up with those estimates. I don't have anything off the top of my head, because it really depends on where you're talking about. You could have a different frequency of hazardous weather in one place just south of Block Island that isn't even close to the same frequency as a place just east of New Jersey, just due to the nature and track of storms. But what we do is we never just use one data set to conduct a resource or a downtime assessment. We have our own internal data set, which is an archive of all the models that we run here, which are fine-tuned. They meet a level of accuracy in terms of a short-term forecast that we would consider it to be acceptable for a historical or climatological data set. And then we look at some of the more popular global versions like the CFS or the ERA, and we often see differences there's some new stuff that's coming out in terms of looking at the rapid refresh initializations, which is a complex thing that NOAA does with the HRRR model. And what you see when you start to look at these different data sets is that you start to see the holes that exist in some of the more global one-size-fits-all data sets that are most popular in the industry. Like I said, the ERA5, right away you start to see that it will underdo peak wind events. And so the frequency that it will give you if you just look at that data at face value is actually not really as high as it is in nature. And we start to see that when we look at more of the high resolution models. And there's reasons for that. But a lot of it comes down to microscale conditions. Winds and thunderstorms, for example, are not going to be predicted by a global model like the ERA5 reanalysis. More observations is the best thing we can do to improve those resource assessments. But the technology and the modeling is definitely improving at a pretty rapid rate right now to come up with those assessments of how often can we inspect hazardous conditions.
I'm kind of going to dive into that kind of question around data. And, New York has invested and deployed mid-ocean buoys offshore, and people are interested in, what kinds of data sources do you rely on for modeling? And then what other organizations do you partner with on kind of data visualization and that kind of part of the product?
So when it comes to visualization, we do everything here. We run our models here, we post-process them, we have a team. Our entire IT department is actually, they're also meteorologists and have IT expertise. So we had to search really hard to find people that were capable of being a network administrator, but also had a degree in meteorology. And so they're particularly talented in coming up with visualization of our products. The data that we run in-house that's our primary source for most of our forecasting, our real-time forecasting. A lot of that, so the initial part of that data, the initial part of our model runs are coming from NOAA models typically, which give you what's called the GDAS initial state, which comes out 4 times a day. But they also offer initial state that comes out every 1 hour for the rapid refresh. So NOAA is really good at providing the tools that are required to run your own models, providing satellite data, reliable servers to get that data. We definitely rely on not just them, but the Europeans. EUMETSAT is a great organization. We have access to a lot of their satellite data. As I said earlier in the presentation, Germany, the weather service of Germany has a great microscale, mesoscale model called Icing. We utilize that. We found that actually to be very useful for the fjords of Norway. It's very good at predicting what the winds are down at the bottom of the fjord as opposed to just outside the fjord. It does a better job than most of the other models that we've tried to use for that. And so we download and process terabytes of data and upload probably close to that on a daily basis. The amount of data that we're bringing in, combined with the amount of data that we're producing, and then the amount of data that we're putting back out is on the order of terabytes a day. And it's amazing that this was not even possible, what we're doing here 10 years ago. The data infrastructure was just not there. Storage has become exponentially cheaper. You have fiber optic internet now, so you can send a full resolution, high or large file to someone else or to another server in a matter of seconds. And when it comes to meteorology, I think the key to success in especially ocean forecasting is the data, because the ocean is a vast empty place that really has a lack of observations. The number of observations that you get on land are probably somewhere on the order of 50 times more per square area. And so satellites are a huge part of what we do. Satellites can measure wind speed at the ocean surface. They can measure wave height at the ocean surface now, which are things that were not possible even 15 years ago. And all of these factors, all of this data gets put into one central place for us here so that we can compare. This is what the model says. This is what the satellite sees. This is what the observation is. And that really is what enables our forecasters to do their job.
Yep, and going off of what Brandon's saying on that too is absolutely, hit the nail on the head with that. Local observations too, such as METAR reports and buoy data, are also taken into account. Again, we have a team of degreed meteorologists who are looking and interpolating this data and comparing it against live observations, and really using that all to make the best forecasts possible for our clients.
Great, and I think we have time for maybe one last question, and this one puts us back into big picture thinking again. Can you talk a little bit about how climate change has kind of impacted what you've been seeing in the, increasing the number of severe weather events that we've been seeing, or changing the frequency of those events?
Yes, and so you may have noticed earlier in the presentation, I noted that if you were to go to NASA has a website called State of the Ocean. It's an open website. Anybody can look at it. And if you look at the sea surface temperature anomalies worldwide, most of the world, the ocean is warmer than the last 100-year climatological norm. And that's really just a pretty well-known mechanism of the carbon cycle and greenhouse gases. That additional heat that is being produced from the greenhouse gas effect and from the increase in CO2, which has been happening over the last 100 years, that heat ends up in the ocean. And so when we look at the mean temperature of the ocean worldwide, we see the ocean is a 0.5 degrees Celsius up to even 2 or 3 Celsius warmer than the last 100-year normal. That energy then goes into producing storms, hurricanes, tropical storms, and even nor'easters are just cut-off lows. Really, any weather system is going to get energy from the ocean. And so we have globally, we have seen an increase, not just around the East Coast, but everywhere in the intensity and frequency of significant weather events. It seems like every year, every ocean basin in the world, every couple of years, every ocean basin in the world breaks a record for the strongest tropical cyclone ever to occur. The East Pacific, it was Patricia back in 2017. The West Pacific has tied the record several times in the last few years for 155, 165 knot sustained windstorms. But off the east coast of the U.S., we see the same thing. There's been, I'll give you an example, Hurricane Sandy and Hurricane Irene. They created conditions over land over the northeastern United States and along the coast, both storms that would be considered a 1 in 100-year flood or a 1 in 100-year wind speed or 100-year return wind speed. Both storms did that in the course of 3 years. And then the other storm on January 4th, 2018, that broke a record for the strongest non-tropical and fastest strengthening coastal low, in observable history, which is pretty much over the last 100 years. Things are definitely increasing in frequency and increasing in intensity. Where does that end, or does it get worse? That's for climate researchers to answer. All I can tell you from our perspective, because we're watching the weather every day, is yes, it's definitely happening more often.
Thank you so much. And before we jump to our closing slide, I wanted to make sure that we put up your contact information one more time, because there was a request in the Q&A for your contact information.
I can do that for you. Here. Just give me 1 second. All right, that will be right here.
All right, and then maybe if you can go to, we'll pause here to let people copy this down. But again, sure. I want to remind everyone that the webinar recording and presentation slides will be available at nyserda.ny.gov /osw-webinar-series. And maybe if you're able to, Brandon, go to the next slide.
Yes.
All right, thank you. Our next webinar in the series is on May 11th at 1 p.m. Noe with DNV Offshore Wind North America will be speaking about vessel types for offshore wind. And you can register for future webinars through our events page at win.ny.gov. If you have any requests for future topics that you would like to hear about in this series, please be sure to email us at offshorewind@nyserda.ny.gov. And again, thank you, Brandon and Donald, for your presentation. And thank you, everyone, for joining us today. See you next time.
Thank you. Our pleasure.